Next up is a classic problem in this particular course, this introductory mechanics course. It's called the ballistic pendulum, if you can decipher that. And this is a method that people actually used to use to measure the speed of a bullet. Back before high-speed photography or videography and modern electronics, this was a pretty reliable way of determining the speed of a round out of a gun. So let me talk about the basic principle, and then I actually found a video on YouTube of some guy in Idaho using an old-fashioned ballistic pendulum to calculate the speed of a round out of his rifle. You've got a massless string, which is free to swing from this pivot up top. At the bottom of the string is something like a wooden block, and I'll call the mass of the block capital M. Here comes a little bullet, as Elmer Fudd says. I will label the mass of the bullet with little m. And let's decide on some times here. So T0 will be the time or the moment just before the bullet lodges in the block. Since it's made out of something like wood, we don't anticipate that the bullet will go right through the block. It will burrow itself into the block, and then the two will be stuck together. And you can imagine that a very fast-moving bullet would lodge in the block and give it enough kinetic energy, let's say, to swing upwards by some amount. So I'll draw a dashed line to indicate this is happening at some later time. Here's the block at that later time with the bullet inside, and it's going to swing up to some maximum angle, which I will label theta, before it comes back down. So the three relevant times would be the moment just before the bullet lodges in the block, and then there's the moment just after lodging in the block. But, and this is important, before swinging upwards. So realistically, this block would begin to swing upwards as soon as the bullet hits it. So while the bullet is still burrowing into the block is already swinging upwards. But the time it takes the bullet to enter the block is really short compared to the time it takes the block to swing to its maximum height. So let's just assume that the two collide first, the bullet lodges in the block first, and then together they swing upwards. And I'm looking at the two times just before lodging in the block and just after, but before swinging upwards. And then the last time here, T2, I'll just say the top of the swing. And the block is momentarily at rest. Okay, so the block will reach its highest point and then swing back down. T2 is the time at which that highest point is achieved. This problem is a nice way to apply principles from chapter 11 and chapter 10 because it requires two conservation principles. We will have to use the conservation of mechanical energy and the conservation of momentum. So why don't we start with applying the conservation of momentum? Okay, conservation of P. And remember, momentum is not always a conserved quantity. What has to be true? Well, if you ever forget, just look at our new way of writing. Newton's second law. Force is the time derivative of momentum. So if there is no force, there is no change in momentum. Now, this is a vector equation, so you can apply it separately, or you should apply it separately. Oops. Along each axis. And I'm going to think of this as the x-axis for this problem. And you know, this is usually when we write this equation, we're referring to a single particle, but I'm now using this equation applied to the system of mass and, excuse me, of block and bullet. So it's true that the block will exert a very large force on the, I'm having trouble here. The bullet will exert a very large force on the block as it enters the block and vice versa because of Newton's third law. But those are internal forces. Those are forces between parts of the system. I don't see any forces from outside. Now, you may recognize that there is a force here, tension, that's directed upwards. And then, of course, there's some gravity force downwards. but those are along the vertical direction, and I'm talking about momentum in this direction. Forces along the y-axis have nothing to do with any change in momentum along the x-axis. So I don't see any x forces from the outside. And that means that during the collision, we can argue that momentum is conserved. Now, before the bullet strikes the block is just chilling. It's just hanging there. So its momentum would have a value of 0. Here comes the bullet with a large positive momentum because it's to the right. And I'm going to argue that that momentum should still be there after the collision. And because this is a one-dimensional problem, at least this phase of the problem, I'm not going to mess with subscripts x and y. So it's understood that I'm applying momentum conservation along the x-axis. Okay, well, when is momentum conserved? It's between these two times that I don't expect the momentum to change. As the block is rising, we could look at the tension and see that it actually does have an x component. So the tension will be changing the momentum of the block on the way up. But we're looking at the time interval before the block starts to swing upwards. So during that time interval, we can argue that the momentum never changes, and that means the total momentum at time 0 should be the total momentum at time 1. I will express that by writing this equation, capital P for total momentum, same before and after. And now, let's just evaluate the various momenta. Initially, remember, this thing has no momentum. The momentum of the bullet, well, we know that momentum is mass times velocity. And I guess I should label my velocities here. So V0, that will be the speed of the bullet at time t0, just before it strikes the block. And then V1 will be the speed of the bullet and the block together. Remember, they move together at T1, which is right after they have finished colliding. And I know that that's a little tough to read there. That says speed of the bullet and the block at T1. Okay, these are just speeds. Those are magnitudes. But remember that momentum is a vector quantity because momentum is proportional to velocity. Velocity is a vector. So it's up to us to assign plus and minus signs as we see fit. If I'm going to call this the positive x-axis, then anything moving to the left would have a negative value of momentum. Since the bullet is moving to the right, it has positive momentum, and I'll just say mass of the bullet times the speed of the bullet at time 0. This is the total momentum because the block's momentum is 0. Now afterwards, because the two objects are moving together, I can treat them as one. They have a shared velocity. We may as well regard them as one mass with equal to a total of big M plus little m. So this is the total mass that's moving right after the collision. And I chose the label V1 for the speed at time 1. So I'm still using the formula mass times velocity, but now it's the combined mass. This is the velocity at time 1 by definition. And I don't have to add a minus sign because obviously we expect the block to be moving to the right. And not only that, but it has to be positive because it's positive before. And the value of the momentum should not change. Okay, so remember the whole point of this exercise or this apparatus really, because this used to get used, the whole point was to solve or calculate the speed of the bullet. So why don't I solve for the speed of the bullet in terms of these other quantities? And here's what I get. So we've already applied one conservation principle. If we had some way of knowing just how fast the block was moving right after the bullet lodged in the block, then we could just plug in the masses and we would know how fast the bullet was going. Of course, you'd also have to know how massive the bullet was, but that's easy. You just put it on a scale. Same for the mass of the block. So that the difficulty is knowing how quickly the block was moving right after the collision. Now, again, if you had a camera that recorded at 500 frames per second, you could just record this and throw it into Tracker or some other analysis software. But the idea is to do this without those modern tools. So let's take a break for a moment and actually watch somebody using a homemade ballistic pendulum. Okay, here's this guy who calls himself, I think his YouTube channel was Mr. Idaho Show. something to that effect. You can see he's on a very large piece of land here, but over here he's got a wooden frame and a pendulum hanging there. You'll see an up-close shot in a moment. I think this thing is made out of metal, but there's a little dial here and a needle that gets pushed up while the weight is swinging. And then the needle stops at its highest point and serves as a record of what that maximum angle was. Let's just watch here. After that is close up. I don't know if you saw that, but this indicator here was down originally, and it got pushed up by, there must be a notch here. Yeah, you can see the notch. And the rod from which the pendulum is hanging, the rod pushes on that notch. And I think you see how that works. Let's back up and watch that once again in slow-mo. Now, as I'm looking at this, I'm realizing this thing does not actually catch the bullet, does it? But does that really affect the calculations by much? Let's go back to the notes here. So his ballistic pendulum doesn't include the bullet, so you would have to leave out this little m. It's only the well, actually, an accurate analysis would account for the fact that the bullet actually flies backwards, but how fast does it really fly backwards? Once it hits that piece of metal, it's not going very fast when it ricochets. Certainly not as fast as it came out the rifle. So that term is rather negligible. There's not a whole lot of loss of accuracy by leaving out this little M here. If we're talking about a metal catcher, even though it didn't really catch the bullet, a metal catcher of even 5 kilograms compared to what, 10 grams? Let's see here. 10 grams divided by 5,000 grams, that's 1/500. It's not going to make a huge difference. I think there are other sources of error here that are even more significant. And you know, we actually were going to do this lab this semester, but let's just pretend that we did. And now we'll finish the analysis by figuring out how to determine this speed based on the angle. And that's going to require just a little bit of trigonometry. You've seen this before, once before, but I'm going to exaggerate the angle here. Let's use, I will use the letter script L for the distance, not the length of the string really, but the distance from the pivot to the center of the block. That's really L. Because when it comes to talking about potential energy, we would use the y coordinate of the center of the block. Okay, so here's a dotted line showing the horizontal height to which the catcher rises. And I'm going to put the origin down here. The origin corresponds to the lowest point of the center of mass of the block, really of the block bullet system. And on its way up, as this block bullet system, it's not a very good arc, as it's swinging upwards, let's look at the various forces involved. I'll pick a point in the middle here. So here's some time in the middle of the swing. Well, the velocity, the instantaneous velocity is always tangent to the trajectory. So right here, the instantaneous velocity would be in that direction. And we know that the string is pulling towards the pivot point. So the tension is directed that way. And then we've got gravity. So I really only see two forces doing work on this block bullet system: tension and gravity. If we were to apply this equation, we'd have to account for the work done by gravity and the work done by tension. But check it out. The work done by tension, well, remember, that's always, you do the line integral of force dotted with displacement, dot the tension with dr at every step along the displacement, and integrate that quantity. Tension is always perpendicular to the displacement. So that work is 0, and we don't even have to worry about it. In fact, since that's the only non-conservative force in this problem, we're not worried about air drag. It's true, air drag would sap a little bit of mechanical energy from the system, but this catcher is not going to be moving very fast. That means there are no so-called external forces. Remember from chapter 10, your book calls any force an external force if it is not gravity and not springs. Those are conservative forces. And if it's also not thermal energy, not dissipative forces, and not, I think that was it. So I could use this equation. Work external equals the change in total energy. Well, there are two contributions. There's a possible increase in thermal energy and then a change in mechanical energy. And for the reasons just stated, this quantity is 0 for this particular problem. And because we're not worried about air drag or friction, there shouldn't be any dissipation of thermal energy because only friction and air drag, kinetic friction, are responsible for dissipated thermal energy. So what we're really saying is that the mechanical energy is conserved. Here's our second conservation principle. This is equivalent to saying that the total energy at time, well, let's see, which two times are we talking about now? If we look back at how the problem was set up, there really is a very large loss of energy during the collision. Think about that. Don't you think quite a bit of the bullet's kinetic energy is going to be dissipated as heat or thermal energy within the block? I'm willing to bet that that block's going to get a little warm. So some of the energy, mechanical energy, is lost in that manner. But it also takes energy to shred the wood inside. I think you can't do that for free. Quite a bit of energy will be used up in burrowing into the wood. So there's a definite loss of energy during the collision. In other words, there's definitely work done by external forces, or you could say dissipated thermal energy. But we're not talking about that time interval. We're talking about the time between right after the bullet has burrowed into the wood and the time when it reaches the top of its trajectory. So the loss of mechanical energy has already taken place during the collision, and now we're going to argue that mechanical energy is conserved during the upward swing. So the two times I'm talking about would be 1 and 2. Total energy at time 1 is total energy at time 2. Okay, and I'm being sloppy with the notation because really this is the total mechanical energy at time 1, total mechanical energy at time 2. Your book likes to use E for the sum of mechanical energy and thermal energy. I'm not crazy about that convention because that forces us to keep writing MECH, but it's understood I am now talking about mechanical energy. Well, we've got two types, kinetic and potential. So you could start here. This is a perfectly valid place to start this problem. To be thorough, you'd want to make a statement about how there's no non-conservative forces at work, and that's why the mechanical energy should be conserved. You probably want to include that in your solution of the problem. Now, can we cross any of these terms out? Due to my choice of origin, when this block is at the bottom of the swing, its center of mass has a y-coordinate of 0. So when we go to use our formula for gravitational energy, you plug in a value of 0, you find that the value of the potential energy at time 1, that's at the bottom of the swing, but after the collision, that potential energy has a value of 0. So I can cross that out. Now, if you would put the origin somewhere else, like up here at the pivot, which is fine, then your potential energy would not be 0, it would be some negative number. Also, the idea is when the block gets to the top of its swing, it pauses for a moment before it comes back down. So the kinetic energy at that moment is 0. And here's an interesting statement that we arrive at. I find that the kinetic energy that the block bullet system has right after the collision, all of that energy will be transformed into potential energy. In fact, that would even be a valid place to start this problem. The logic is very clear. You could say, well, since we put the origin here, the only energy we've got is kinetic, and it will all be transformed into potential by the time the block gets to the top of the swing. So even this would have been a fine place to start. Now let's go ahead and evaluate. 1/2 mv squared, where the total mass is block plus the bullet. There's the V1 that we're looking for. And at the top, we use this formula. Total mass of big M plus little m, g, so I'm using mgy, but now we need the y coordinate of the top here. So I'm going to call this Y1. This is the height of the center of mass of that system at time 1. And how do we get that? Well, this is already pretty cluttered, but let's look at this right triangle. You've seen this geometry before. What we need is this distance right here. If we could take this total distance from the bottom point of the center of mass to the pivot and subtract the adjacent side of this triangle, and remember this is theta, the maximum angle is theta. So take this distance and subtract the adjacent side of this triangle, we would have this. That's what we're interested in. Well, this is just the length L. By definition, L goes from the pivot to the center of mass of the block. So take the distance L and then subtract the adjacent side. But what is the adjacent side? Look at the hypotenuse here. This is also L, pivot to center of mass. So if we take hypotenuse L and multiply by the cosine of theta, we get the adjacent side. So, whoops. In other words, L minus L cos theta. That is the length. Oops. That's this distance right here, Y1. And we could factor out the L, right? So I'm going to write this as L times 1 minus cos theta. So that's one of the only difficulties here is figuring out how to express the final Y coordinate of the center of mass. And you'll notice that it doesn't seem to matter what the mass of the block or bullet is. That crosses out. And I do need V1 to the first power, not V1 squared. Pardon me. So I'm going to solve this for V1. And we get this all too familiar root 2g times a height, like root 2gh, root 2g L times 1 minus cos theta. All right, let's take this result. So we've determined the speed of the block bullet system right after the collision in terms of the length of the rod in the video and the final angle to which the pendulum rises. Makes sense, right? The higher the angle, the faster you would expect the speed to come out. Same thing for the length of the rod. A longer rod that rises to the same angle, well, that would mean a greater rise in height. I'll substitute this in here, and I find that the bullet speed, in terms of everything else, should be this expression. Root 2gl 1 minus cos theta. So all that must be done is a determination of theta. That's what the indicator did in that video. A measurement of L and a measurement of the masses. And that you can do with the scale. Pretty cool, huh? No need for high-speed cameras or modern electronic timing equipment. Now, perhaps we should do an example here. Yeah, let's try something. Here's another use of this formula. Suppose what you're told is that the bullet's mass is 10 grams. I think that's a typical mass for a round, a bullet. And that the metal catcher or wooden block is a modest 2 kilograms. And maybe the length of the pendulum or the distance from pivot to center of mass is only 60 centimeters. And the bullet's coming out a little faster than sound. We know bullets can go faster than sound. So this is not like a high-powered sniper rifle round. I don't know if I'm using the correct terminology there, but bullets can definitely go faster than this. In fact, I think they can go well over 1,000 meters per second. So that would be like Mach 3 or 4. Given these quantities, find theta. So can you anticipate ahead of time? Instead of solving for the speed, what if you knew already how fast the bullet comes out of the rifle? Could you anticipate how high the pendulum will rise before coming to a stop and falling back down? Well, that amounts to solving this equation for theta. So maybe you should pause, take a moment and try this on your own if you'd like. Here's what I find when I invert this formula for theta. I find that theta would have to be the arc cosine of 1 minus mass of the bullet, speed of the bullet initially squared over 2gl. Okay, I didn't just do that all in my head. I already had that worked out. See that? I wrote this out already, but My writing was too small, so I couldn't use this piece of paper for this video. Now the writing's bigger, but sloppier. I find that when I plug these numbers in, now let's think for a moment. If the bullet was going way faster than this, like, 5,000 miles per hour, and the bullet was real heavy, and your catcher was not particularly heavy, you might expect that the bullet would be going fast enough to make this thing just clear the apex, just go all the way around, and then start do multiple turns before friction brings it to a stop. Of course, you can imagine circumstances in which the catcher would get knocked clear past 180 degrees. But the numbers I've chosen here are typical. So if you try to use your intuition, common sense, whatever you want to call it, you wouldn't expect the angle to be too large. And I find that it comes out to be 62 degrees. So that's a little satisfying to see that at least it's in the range of reasonable values. Okay, and let me show the YouTube channel in case you want to go back and watch that guy. Okay, not Mr. Idaho Man, the Idahoan Show. The first time I've seen a homemade ballistic pendulum.